Hi everyone, I'm Amir Hossein. Before using RTTOV model or the RTTOVpy software, we need to understand the physics behind them. Satellites do not directly measure temperature, humidity, or cloud height. They measure electromagnetic radiation arriving at the sensor. Radiative transfer explains how that radiation is emitted, absorbed, transmitted, reflected, and scattered on its way through the atmosphere. The quantity a satellite measures is radiance, radiation traveling in a particular direction within a particular spectral interval. As this scene shows, the signal at the sensor is a mixture. In red, thermal emission from the surface. In orange, emission from the atmosphere itself. In yellow, reflected sunlight. In purple, radiation is scattered into the view by aerosols or clouds. And along the way, some radiation is absorbed or scattered out of the path. The satellite only sees the final sum, so the central question is, if we know the atmospheric and surface conditions, what radiance will the satellite observe? What is the forward radiation transfer problem? The problem RTTOV solves. Electromagnetic radiation can be described by wavelength, frequency, or wave number, with shorter wavelengths meaning higher frequencies. Different channels observe different regions of the spectrum. Visible channels measure reflected sunlight, so they work mainly in daytime. Near-infrared channels add information about vegetation, snow, and surface properties. Thermal infrared channels measure emission from the Earth and atmosphere, day and night. Microwave channels at longer wavelengths are key for temperature and humidity sounding and can often see through clouds. One important detail: a channel never measures a single wavelength. It responds over a spectral range described by its spectral response function, and the measured radiance is a weighted average across that interval. Every object above absolute zero emits radiation, described in the ideal case by Planck's law. Hotter objects emit more, and their peak shifts to shorter wavelengths. You can see that here the Sun near 5800 Kelvin peaks in the visible wavelength. The Earth near 288 Kelvin peaks in the thermal infrared wavelength around 10 micrometers. Real surfaces are not perfect black bodies. Their emissivity between 0 and 1 depends on wavelength and surface type. Water, soil, snow, and deserts all differ. Thermal measurements are often expressed as brightness temperature, the temperature a black body would need to produce the observed radiance. It is not always the physical temperature. A window channel may see the surface. An absorbing channel sees colder layers aloft, and one opaque cloud gives its cloud top temperature. As radiation crosses the atmosphere, four processes occur. Transmission. Radiation passes through a layer. The fraction passing through is the transmittance, from 1 for complete transmission to 0 for none. Absorption. Gases and particles take energy from the radiation. Each gas absorbs at characteristic wavelengths. Water vapor in the infrared and microwave, carbon dioxide and ozone in the infrared. These differences let channels target specific gases and layers. Emission. A layer that absorbs also emits, and warmer layers emit more. The satellite signal contains contributions from many layers. Scattering. The direction of radiation changes. It matters most for visible light, clouds, aerosols, and precipitation. In clear sky, thermal infrared, it can often be neglected. With clouds or aerosols, it cannot. Attenuation is described by optical depth. Small means transparent, Large means strongly attenuated. The Beer-Lambert law links the two. Transmittance is the exponential of minus the optical depth. Models divide the atmosphere into layers, each with its own pressure, temperature, humidity, gases, clouds, and aerosols. Follow the red arrow. Surface emission passes through every layer above and weakens on the way, while each layer adds its own emission. The orange arrows, the radiance crossing the top of the atmosphere is combined contribution of the surface and all layers. Absorption varies strongly within wavelength. Relatively transparent regions are called atmospheric windows. The thermal infrared between about 8 and 12 micrometers is an important one, sensitive mainly to the surface and cloud tops. Absorption channels sit inside gas absorption bands, where the signal comes mainly from the atmosphere. Weak absorption senses low layers. Weak absorption senses low layers. A strong absorption senses high layers, the principle behind satellite sounding. The channel's vertical sensitivity is its weighting function, shown in this panel. The window channel peaks at the surface, the absorption channel peaks in the mid-atmosphere. The radiative transfer equation says the change in radiance along the path equals radiation added minus radiation removed. In the simple thermal case without a scattering, dI by ds equals minus Ki plus Kd. Absorption removes radiation, thermal emission adds it. At the top of the atmosphere, the result combines transmitted surface emission, atmospheric emission, surface reflected downward radiation, and in daytime, reflected sunlight. Larger viewing angles mean longer paths, more absorption, less transmittance. The forward problem, the upper path, the atmospheric and surface states are known, and we compute the simulated radiance. This is RTTOV. The inverse problem runs the other way, from measured radiances back to the atmospheric properties. It is harder, because different states can produce similar radiances and measurements contain noise. This is why forward models are central to data assimilation. The model atmosphere goes into RTTOV, simulated radiances are compared with real observations, and the differences correct the model state. RTTOV is the bridge between model variables and satellite observations. It also has to be fast. Line-by-line models are accurate but slow. Operational centers simulate millions of observations. RTTOV uses pre-computed coefficients to approximate them efficiently, and also provides transmittances and Jacobians, the sensitivities that retrieval and assimilation systems need. ERA5 and WRF outputs are not stored in the profile format RTTOV needs. Variables must be extracted, converted, and combined, and the right instrument, channels, and coefficients selected. RTTOVpy software handles this workflow. As the pipeline shows, model fields enter at the top. RTTOVpy prepares the profiles, runs the RTTOV simulation, and post-processes the results into netcdf files and synthetic imagery. Verification against real satellite observations is built in, a direct comparison in observation space with statistics such as Taylor diagrams. RTTOVpy does not replace RTTOV, it wraps a practical workflow around it. To summarize, satellites measure radiance, not atmospheric variables. The atmosphere absorbs, emits, transmits, and scatters radiation, depending strongly on wavelength. Window channels see the surface, absorption channels see atmospheric layers. RTTOV solves the forward problem quickly, and RTTOVpy software makes it practical.